So today we are going to talk about sorting under partial information. So I'm going to base this presentation on an article which is called Sorting Under Partial Information without ellipsoid algorithm. This is by a lot of people. The first author is Cardinal. And so this ellipsoid algorithm is what I understood from a complicated algorithm. And so this is what I'm going to present is technique of proofs that are able to avoid this ellipsoid algorithm. And this technique of proof actually are practical if you want to show that your algorithm is in big O of n log. Anyway, so first we need to define what is sorting under partial information. So if you don't have just sorting is just to sort things. So this everyone knows. Sorting under partial information is just that you consider that at the beginning you have more information. And what you consider is that you have already a partially ordered set. So for example, consider that you have 5 items and then one possible adding of information, one possible set, a partially ordered set, would be that you have, for example, this. So you already know that A is bigger than B. Okay, so this is sorting under partial information. You already have information at the beginning that is given to you in the form of a partially ordered process. Okay, so here I need to introduce a bit of vocabulary. So if you have a process P, the set of all possible compatible orders is called the set of linear extensions. Okay, and the number of linear extension is called E of P. Okay, so first, when you have sorting under partial information, you know that you need to do at most, E of P operations, because it's all the compatible linear extensions. And so, because if you test every possible, one algorithm could be to test every possible linear extension and to say if they are yes or no, the order we want. And so this quantity here is what is going to be interesting for us, and we want to be able to sort in less than this. Okay, and so to do this, we are going to introduce something that is called graph entropy. And this graph entropy, we're going to apply it to our process. So the graph entropy.
So E of P is the number of linear extensions compatible with the partial order.
Yeah, that's it. Okay, so graph entropy H is I need to introduce other stuff before giving you the definition of H. So consider you have a graph. Okay, for example, that could look like this. Then you want to take an independent set. So an independent set is just a set of vertices that are not linked to every other. So for example, this set S right here, or maybe in some lines. So A, B, and D here is an independent set because none of them is linked to one another. And so you take all these kind of sets. So for S, you are going to associate to S this vertex right here. So when you take A, you put 1, and when you don't take a vertex, you put 0. So to S, we associate this vector, vector, and you take all possible vectors like this, and you are going to minimize some quantity on the set of all these vertices. So for example, if we do all the possible vectors here, what do we have? We have 1, 1, 0, 1, 1, 1. No, not this one, sorry. We have, for example, 0, 1, 1, because you don't take A, but you just take B, C, D, etc., etc. You don't necessarily take maximum sets. For example, a valid example could be just 1, 0, 0, 0. Just take A. This is an independent set. And so you take all these sets and you minimize some quantity. So what you minimize here.
Just a question, the empty graph is a solution also?
What?
0 everywhere.
Yes, because you will see that actually if you take it up now or not, it will not change the result. But yeah, the empty set. Oh yeah, and I forgot that. I told that you minimize on this set. It's actually the convex envelope of this set. So
convex hull.
Convex hull. But it's not going to change if you take empty set on this, even on the convex hull. And so where is it written? Here, probably. Okay, here. So H of G is 1 for every So H of G is the minimum of every vector in the convex hull of the independent set of this quantity minus 1 over n, sorry. This is the size of the poset. Okay, so here, for example, it will be minus 1 over 4 of every vertex in the poset of log of x of b. So this is just the every component of the vector. So for example, for this vector, you would have xa, xb, xc, xd. Okay. And so for example, you see that here you have 0, this tends to minus infinity, so this tends to plus infinity, and so you know for sure that every of the vertices, every one of these vectors here will not satisfy the main condition. And so in particular, if you have 0, 0, 0, this quantity here is equal to plus infinity. So that's why if you take it or not, it will not change the result here.
There is something I missed. What does it mean, log of vector?
It's log of the components. So here you have xa, xb, xc.
Okay.
Okay. So here if you take one of these vectors here, you will always have plus infinity here, because you will have some zeros. Except if you take this graph here, because then this is possible, and so you will have zeros here.
What is n?
This is the size of the poset. So for this poset, for example, it would be 4.
So that's a constant.
It's the number of nodes.
Yeah. But
Yeah, it's
basically
just the
for
number
the
of
graph,
items.
It's
you
the size
have
of the
to
graph, the number of nodes.
you could bring it outside of the min.
Yeah, you could. Okay. And so this is
That means the middle, so you have some values that are
okay. This is the definition in the case where you take a graph, quelconque. But in our case, we are going to apply this to our poset. And so we are going to apply this to the graph of incomparability. So for example, let's say that
Before we go to
Yeah.
so why is it called graph entropy? So entropy is
okay, so at the beginning, this was not used for sorting. The entropy was defined to calculate how a random variable was random and how it could surprise us. And then they found a way to represent this entropy for random variables with graphs. And so this was the definition that followed from this representation. And so there's an equivalence between the graph entropy for random variables and the graph entropy for the graph.
okay, so but the graph is not a random graph here, so it's a deterministic graph.
Yeah.
And so I don't see the connection between the entropy of a random variable and the entropy of that you defined here. So
I don't know this connection. I haven't read all the bibliography, but I know that they had a random variable. They represent it in some sort of graph, and then probably, I think it's probably random variables on discrete set. And so probably these vertices are all the possible values for the random variable, and probably you do some links between these values. But the random variable part, I haven't studied it yet. I just know that this definition is derived from the random variable.
and okay, and so you have these independent sets which are linked to the graph. And so, I mean, could you explain? You gave one case where this thing is not infinite, which is the graph with no edges, right?
Yeah.
But are there other cases where the entropy is finite?
Yeah, it's always finite, actually.
Sorry,
Always.
Yeah.
it's always finite,
Yeah.
and
Because you take the convex
the convex
of
part.
the independent set.
Okay, and so you would have points which are halfway, which
Yeah.
For
on
instance,
the
you always
set.
have the point 1/n.
is what I was thinking.
Yeah.
Okay,
So you know that there is a point with entropy log of n, and just depending on the structure, you might find better points.
okay, but I'm still puzzled. I mean, you cannot name anything entropy, right? So
It's a trademark.
otherwise, about
L'espace pour faire un.
There's an interpretation that brings it back to entropy. I'm Wikipediaing this. So basically, if your graph represents symbols, vertices are symbols and edges show symbols that can be mixed up, that are indistinguishable, then there's some notion of how much information you can encode with those symbols given that mixing. which brings it back to information theory.
This is what Deria was discussing. Right? So she gave a lecture about the erasure channel. And so if you can mix up things you don't know, so it's linked to that, right?
Reduces your information throughput. And that's sort of what we're measuring up.
Okay.
I'll keep it there because that's all I understood in 3 lines of Wikipedia.
Okay, but she was discussing something which was related, if I remember well.
There's a good interpretation.
But yeah, if I can make a stab at it, if you take the empty graph with no edges, its entropy is 0. And according to your interpretation, that means that you can encode anything and you will not lose any information with that. If you take the complete graph, its entropy will be log of n, which means that you will lose kind of log of n information. And given that the information of taking a random signal among n characters is also log of n, basically that means that you will destroy all your information. So it's an entropy that is taken from the input signal.
Okay, the complete graph would be the case where you can confuse any symbol
Yes,
with any other,
exactly.
right? And so it's like you toss at random uniformly and n, and therefore
But you cannot do anything from it.
you cannot retrieve it.
You've got an entropy log of n that is deduced in terms of quantity of information.
Okay, so this is some sort of entropy then of random variable. So if you would take 1 point on the graph at random, perhaps it is linked to and to have this confusion with the graph being describing confusion between symbols that can be linked to the entropy of something like that. Okay, I get it. Not completely, but thank you. Sorry for interruption.
No, it's okay. So what is it? Yeah, so here, this is the definition for graphs in general, but for the case of posets and of sorting, we are going to apply this to what we call the graph of incomparability. So let's say that your poset is this, so you know that A is greater than B, and you don't know anything about C. Then your graph, so here, this is the poset, and the graph of incomparability is this. So you still have A, B, and C, but then N, A, C, they are not comparable. So you put an edge here, same for B and C. And here, what you can see is that this is an independent set, and this corresponds to a chain. So for example, if we add vertices here, the graph of incomparability will be this, and so this here is a chain in the initial process. So when you have a chain in a poset, you have an independent set in the graph of incomparability. Okay. One other possible thing would be, for example, just C. Okay. Just C is a chain here, and just C is an independent set here. And so when it comes to posets, this set right here will be still the convex pole of the chains in P. Okay, and so this will help us to have some intuition on how this entropy moves when we add information here. Okay. So maybe we can do some example to see how this entropy will be calculated and will move when we add some edges. So the example we're going to do this one. So we have two chains of size 5. So here A, B, C, D, 5. Okay, so these chains here will be represented as a vector like so. This chain, let's call this chain 1 and chain 2. Chain 1. C1 is represented as like this vector in the graph of incomparability, and C2 is represented by this vector. And so now you see that if you take a convex point between those 2 points, oh yeah, I forgot to mention that here you minimize on the chains in P, but this is equivalent to minimize on the maximum chains.
I have a question.
And so here, if you only take those 2 vectors, you just have to minimize on the convex point between those 2 vectors. And so what you need to minimize is a vector is something that will use this vector. So what you need to minimize here, if you take this, yeah. So, one minus alpha. So this is the quantity you want to minimize here, okay? Because you have 5 times alpha and 5 times 1 minus alpha. Okay, so these alpha are these components. So you have and here you see that if you take 2 chains, it's always going to be this and that. It's independent from this size, but it's just a remark. It's not really What?
Is it? No, because it's equivalent with on an independent set of incompatibility graph.
Yeah.
And on the chains
Got it.
of opposite.
Yeah. And the maximal independent set of the incomparability graph
Is the
precisely
maximal
corresponds to the
chain.
maximal set.
And so that's why
Of the
here
So,
the entropy
Yeah.
But it's just that it's easier to figure the poset and do the math on the incomparability graph. So it may be a bit confusing, but okay, so now we derive this, and we have alpha. Yeah. Alpha. Yeah. So.
yes, something like that.
And so you have it's this equal to 0. And we find alpha is
1/2. It's essentially by symmetry.
By symmetry,
Around
it should be 0 or 1 or 1/2.
Yeah.
And 1/2 is
and so then h of this process is minus 1/2 divided by 1/2 okay, 1/2, which is 1. Okay.
What?
Yeah, I think so.
It's not base 2, it's base 2.
Logarithm
Yeah,
is-
yeah.
Take the right log it is.
So civilized log.
This is the civilized one.
Log base.
The only civilized one.
Okay, so the entropy for 2 chains is always 1. And now,
2 chains of equal size.
yeah, 2 chains of equal size. Now, let's add some information. Let's, for example, say now I know how to compare E and G, and let's say that E is greater than G. So now the maximal chains here are
Need to add J to C1.
yeah, C3. So C1 is this one.
You just
C2 is
modify
this
C1.
one,
Just
and
modify C1.
C3.
No, you still have only 2 chains.
For this one, you only have
Yeah.
to.
Because I
You're
haven't
anticipate.
already-
You're anticipating for the next example.
Okay, so J. So you just add 1 here. And then here you will have a 1, okay, because it's going to be alpha plus 1 minus alpha. And so, remember I said before that this example is, so this is 1 whenever the size, no matter the size of the chains here, as long as they are equal. Okay, because here you can see that it's always be n/2 divided by n. And so I'm going to do my example in the case where we have a coset of size n. So here, instead of 5/10, it's going to be n/2 divided by n. And here, n/2 minus 1 divided by n.
By n minus 1, I guess. In
No.
both cases, it's divided by n minus 1.
Wow.
Why?
Here, n.
Sorry, it is the n. Sorry, it's the n of the entropy. Sorry.
And so. What am I supposed to do next?
So
I just need to grab
if you want, Emma, I just did the calculation. So if you want, as you like it.
You want to do it?
If you want.
Okay.
Okay. My turn. I put you in this bad situation. I'm going to try to.
Don't erase this.
Okay, so I'm not going to erase this. I'm going to erase this. Okay, so just for the following, it will be convenient to treat the general case where, in fact, we have alpha a number of times a, 1 minus alpha a number of times b, and 1 a number of times c, which will be equal to n minus a and b. And just because I'm lazy, I'm going to denote this f, which is just the sum of the logarithms that we want to maximize. Okay, so in this case, I will have f, which is equal to a times log of alpha plus b log of 1 minus alpha plus c times log of 1, which can be ignored. And then when I derive this, I will have something like a over alpha plus b over 1 minus alpha. And when I solve this, we have something so which will take equal to 0. So a sorry, minus no is equal to b over 1 minus alpha. So A times 1 minus alpha is equal to B times alpha, which is a minus, sorry, 30. And then A is equal to alpha times B minus A, and then alpha is equal to A over B minus A plus A, probably. Yeah. It is the Banafio school. I made a wrong computation and then I correct the results. Then I will have F, which is going to be equal to A log of A over A plus B log of, and of course it's symmetric. Okay, so this is going to be my optimal F.
And if you want, you can
And here you can divide by n, then you have
And
okay,
so
A plus B plus
let's go minus
A plus B plus n equal to A plus B plus
A over A plus B minus B over N log of B over A plus B. Okay, so that will give
just F, as you said, it's entropy of A plus entropy of B minus entropy of A plus B.
yes, I could. I could and I won't. Okay, so now maybe I'm just going to erase the computation and just record the results. Minus A over N log of A over A plus B minus B over N log of B over A plus B. Okay, so that's our starting point for this kind of cases. Okay, so now, okay. So let us treat now the case. So basically the question is, okay, you want to sort this based on this partial information. And the kind of questions that we might want to answer is it better from the point of view of information to ask the comparison between these two elements, for example? Or is it better to ask for the comparison between the two elements in the middle? What would you guess? I will make a middle and bottom. Remy, what do you think is better? So just from the point of view of gaining information, because in the end you want to sort the whole set. From the point of view of information, will it be better to ask for the comparison between these two elements? So just assume that for the moment you know that. Is it better to ask for the comparison of these two elements or the two elements in the middle of the chains? What would you guess? Bottom, so up, one vote.
I'll go from the middle.
Middle, the geek.
I don't play.
You don't play, of course.
Okay, I would say middle, but it's just a guess.
Okay, people on the bridge, can you answer in the chat? Middle or bottom? What do you think? Bottom. Okay. Middle.
I'll go with middle also.
Okay, so there's a slight majority for middle. Okay, we will see. Okay, so let's start with bottom. So we assume that we compare these two, and for example, we found out that, well, I will lengthen this row a bit just to show, like, easier to show this. Okay, and as Emma mentioned, now we have this number of alpha, this number of 1 minus alpha, and
so A is n over 2, and B here is
yeah,
n over 2 minus 1.
Yes.
So you made the calculation.
Yes.
Yeah, then
Yeah.
just need to
But
apply.
in fact, what we will do because you will see that the expression is not very. So in that case, we will have h, which is equal to sorry, I will still reason in terms of f because
Isn't it the same H? I do not understand why you.
okay, because before we had an additional 1 minus alpha. It was 5 and 5, and now it's 5 and 4. So it will be slightly different. So it falls into that general case, and that's why I did the general case as a general calculation tool for the rest. But when particularizing on this case, it will give, so sorry, I will put the -1/n in factor just to be able to use what I did on my sheet. Plus n minus 1 log of 1. Okay, do you agree with me more or less?
Yeah.
Okay. So I will just do the limited development for the first case. I will not do it for the second one. I will just give you the results. So for this one, we have something like log of 1/2 times n over n minus 1, which is equal to, so log of 1/2 is -1 minus log of n minus 1 over n, which is 1 minus 1 over n, and here it's -1 plus 1 over n plus big O of 1 over n squared. We want to see what happens at least in the case where n is big. Okay. And then here similarly you will have something like a log of 1/2 times n minus 2 over n minus 1, which is -1 plus log of 1 minus 1 over n minus 1, which is -1 minus 1 over n minus 1, but I can write 1 over n because the difference will fall in the big O of n. Okay. And then when you gather all this, I will try to do the whole computation without plotting up. -1 plus 1 over n plus big O of 1 over n squared. Okay. Plus 1 minus 1 minus 1 over n plus big O of 1 over n squared. Do I have the correct number from phases? I think so. No. Up, I'm missing. And then here, minus n over 2 plus 1 over 2 plus big O of 1 over n plus so minus n over 2 plus 1 by 1 is 1 and minus 1 over 2. This one will be in the big O of 1 over n. Okay. 2. So in the end, so I'm going to write this minus n. This is okay. This is okay. Plus 1 plus big O of 1 over n multiplied by minus 1 over n, which plus 1 minus 1 over n plus big O of 1 over n squared. So doing this, so just just for as a reminder, the entropy, the initial entropy was 1. And doing this, we have reduced the entropy by 1/n. That's what we did with the bottom comparison.
And just to put this in the context, remind that the entropy of a complete graph here in our case would be 0 because we look at the graph of incomparability. So that when everyone is comparable, the graph of incomparability is this, and the entropy is 0. When no one is comparable at the beginning, the entropy would be logarithm. So we want to decrease the entropy to 0. So it's actually nice that we decrease it positively.
Okay, so I will just remove the shouldn't have. 1 minus 1/n plus O of 1/n square. So this is for the bottom comparison. Okay. Should you show what is to be maximized in the case where we compare the middle ones, and I will do the calculation.
Yes. We are doing this case now. Okay.
Removing this.
And so now, can I erase this?
Yeah. We know that middle is the winning candidate.
Okay. Maybe I'm going to take
That's
the-
right. Yes, go ahead.
So now we also have this chain here. Okay. So this chain in red.
And this comes back to what it was before.
Yeah. So this is 0 again. C1 is again this. C2 is this. And C3 is this chain. And so we have 1, 1, 1, 0, 0, yeah. 0, 0, 1, 1, 1. So we have a bunch of ones on the extremities and 0 here. And so here we put alpha.
Ah no, it is in direction, it is oriented.
So this one will be 1 minus 2 alpha, please.
1 minus 2 alpha here, and here alpha and alpha.
Okay,
So
so
normally we're supposed to put alpha and beta, but we can do alpha is equal to beta to just simplify the
Yeah.
calculation.
essentially by symmetry, we can assume
Yeah.
that the coefficient for C1 and C2 is the same. So be reassured, I will not do the computation because I don't want to. But essentially, what you will have is something like.
Maybe I can just show how the vertex looks here.
Yes.
Is this right? Yeah.
Yes.
because you have-
Yes. So you have
And
3,
here-
yes, and then alpha in the middle, and then 3, 1 minus 4 of them for your particular case.
Or- oh, yeah.
Yes. And then, yes. Yeah. So in fact, the 4 alpha corresponds to D, E, F, and G, which are not taken in T3.
And so here you have n over 2 plus 1.
And then, yes, you have so here we already see, in fact, that with this version, the entropy will remain higher. Yes, because minus log alpha is positive. So in fact, even before doing the limited development, in fact, we can see that this solution is less good in terms of diminishing the entropy. And in fact, when you do the limited development, so I will spare you the nasty details, but it's essentially, if I'm not mistaken, something like so the paper says it's in a big O of n square, I think, but so I found something with an n square, so I'm not too far from the correct result. So here you find, so here's the for middle. In fact, you diminish the entropy only by something like that is in the order of magnitude of 1/n². So it's not as good as the first solution.
Okay. Thank you, François.
You're welcome.
So yeah, in terms of entropy, graph entropy, it's better to search to do this comparison. In terms of splitting the set of
Just a question, isn't it the same if you are the upper?
yeah, it will be the same if you do the upper comparison. Yeah. So in terms of splitting all the possible linear extensions, it's actually better to do this comparison. So that is just to say that the entropy sometimes does not capture everything that we want, but there's a theorem that I'm going to write you probably here.
Just maybe to rephrase, because it's so counterintuitive that maybe you missed it. In terms of entropy, it's better to take in the bottom, okay? But ideally, intuitively, what you want to do is that here you have a certain number of linear extensions, which are all the possible total orderings of this set. Okay? And in terms of gaining information, what you would like is to split the universe into two different states, where you essentially have half of them and half of them. And that's exactly what the middle split is doing. You split the universe into two halves. In terms of gaining information about the final order, it's excellent. And what it means is that this tool of the entropy of the incomparability graph is just a tool. It's not a perfect tool to tell you what is the best comparison. So in some sense, the people thinking that it's better to split in the middle are right, because it's exactly split the universe into two equal sized states. But this entropy of the incomparability graph will wrongly, in some sense, tell you that it's better to compare the two bottom ones. So you can think about that tonight when going to sleep.
If you cut on the bottom, you split alpha as well.
Yes.
So yes, but in specific case, yeah, they are all equal. All possibilities split the world in two.
Yeah, sorry. Yes, you're right.
It's just that entropy suggests to go bottom.
Yeah.
By far.
Yeah.
Whereas in practice, it's all the same.
Yeah. Yeah, sorry. Yes, you're right.
Entropy relate to that case. What is the meaning of the entropy if it's not just producing how much we don't know?
And you've got to go through it now.
Okay, so to justify that we use the entropy, I'm going to write two theorems so that you understand why we use this. So the first one, where is it?
It's at least related in the sense that when the entropy falls to zero, you're done.
So we can prove that you were able to reduce entropy to zero
relatively quickly, then you will have a proof of quick conversion.
So if your entropy reduces by 1/n, you know that you need n squared.
No, because you start from log of n.
Something like that.
Yes, the entropy of the empty graph is log of n.
Right.
One is just this example, but if by increment of 1/n, want to go to log of n to 0, you need n log of n comparison.
Yeah, which sounds logical.
Yeah.
So the lemma, first lemma, for any coset of size n, this quantity here, the number of extension, is lower than n, the entropy of P, and this is lower than mean of. So the minimum of this quantity, so log E of P plus log of exponential. So here the notation is not perfect, but it's not my notation.
The log on the left is base 2, right?
Yes, I
always.
put 2 here.
I meant the left.
That's what log of E
Yeah.
means.
No.
No, I meant the log of.
No, but that, I mean, no.
Yeah, right.
And
Yeah.
this is 2.
Yeah.
They're all in base 2.
Good enough.
They're all in base 2.
And the notation of the articles.
Yes, they do.
Yes, this is not the.
So,
The number of extensions.
here,
Yeah.
this lemma just states that you can bound this by quantity that are near to log of
Close.
E of P.
So they,
And remember that this is you want to diminish this as much as possible every time you do a comparison. And so if you diminish this H of P quite well, you know that it's not going to be far from this quantity, and you know that this quantity will actually decrease too. Yes.
5 minutes.
and I had do we know that greedy is good? You say every time we diminish by as much as we can, which is a greedy approach. Meh.
Yeah, that's the second theorem actually.
Ah,
I'm going to-
Sorry.
Very good. So the second theorem says that for any process P of size n, there is A and B such that H of P. So this notation, P A smaller than B, is just that to P you added this relation, okay? Here you take the max of H of P. H of P is smaller than this. So this just says that there exists A and B, that if you compare them, this is smaller than H of P minus a positive constant. Okay, so greater than 0. And so if you iterate this, so let's say that after K comparisons,
Just to be clear, Emma, I think that there exists a constant C such that
yeah,
for any poset, no.
Yeah.
And just to be sure that
Is there a value?
we know some values. I think.
yeah, there is some value for C, but it's not important.
Does it end on n?
C does not depend on n.
So it's really
It's really,
at the
yeah,
start.
Yeah,
like here, actually.
yeah, it's really at
For
the
all
beginning.
these-
And for all
Yeah. Yeah, that's very powerful
Okay,
result.
so it's
Yeah.
really.
So it's just to say that after K comparison, you have an entropy that is smaller than after the entropy after K
And when
minus
it's
1
at
minus
C
T.
over N,
Oh, yeah. Not because here, normally. Yeah, you're probably
Ever
right.
you add N
No.
left.
Yes, I'm always puzzled with whether it's defined up to
Yeah, I
a
don't know.
It depends if C depends on n or not. But if it
There's no
doesn't-
n, right? Yeah.
Z over N.
no, it's okay.
It was good for.
H of T at the beginning is log
Yeah,
n.
there's no n here because I normally use n. Or is there an n?
Well, yeah, because with C it wouldn't give the right result in
Yeah.
terms of.
Yes,
So
yeah,
that's-
it's like that. If I compute it by N for me.
If for the worst case, you're supposed to find n log n as the number of iterations.
Yeah.
that's really bad.
Yeah.
Yes, so there's an n.
Yeah.
It's just because in the theorem they put n everywhere here. So
But apparently historically the entropy of a graph is defined without this n constant. And in this application, we really would like the n constant because it would be much more natural to have an entropy in n log n.
So if you iterate this, it means that after K comparison, H of K is smaller than this. And so if you want this to be equal to 0, right? So if you want to solve this, it's just to say that k is equal to
Something like something in
I take it there's something when the entropy becomes 0
Okay.
where that result doesn't work.
Yeah,
You
that's
mentioned
for any
at least
pair.
one pair that can be compared.
Okay, good enough.
So here it means that after k comparisons, so after n log n comparisons divided by c, your entropy will be 0 and you will have sorted your process. And so you see that here, if the c is a positive constant, then you will know that you will sort in big O of n log n. And so the whole point of using the entropy is to say, okay, I have a sorting algorithm for my partially ordered sets. If I'm able to say that after each comparison, my entropy has diminished from a positive constant, then I will be able to prove that my algorithm ends in big O of n log n. Yes.
See if I understand now. The real question is that result constructed? You know how to find that A-B comparison?
Here, this theorem, no, because with the positive constant that they put, it's not linked to an algorithm. But in this paper, they use this technique with their algorithms to prove that it's
So in fact, what they do in the algorithm is that in the paper, sorry, is that they mention 3 algorithms, explicit algorithms. And in fact, they, correct me if I'm wrong, but in fact, they use this kind of technique to say, okay, with algorithm 1, in fact, at each step, I diminish the entropy by so and so, and then I can give guarantees about the termination complexity of the algorithm. So they use this kind of technique very explicitly for real algorithms. And I can just give you the first algorithm that they give. For example, it's very simple to explain. In fact, you take the longest chain of your posets, and then for all the other elements, you will insert them by a binary search in this longest chain. And in fact, you can give with this kind of techniques, you can give guarantees of terminations depending on the initial number of linear extensions, so E of P, initial E of P, which is the number of linear extension of your initial poset. Because since you can bound the initial entropy by something that depends on the number of linear extension, you, instead of saying n log n, yes, n log n is for complete sorting, but here you have initial information. So you can give better bounds than just n log n, depending on the quantity of information.
If you take an algorithm that exists, if it doesn't satisfy that constraint, you don't have that bound straight away, right?
Exactly.
So that bound, if you're using a level 1 and the knowledge of how quickly you're decreasing it, well, you're losing the knowledge of how quickly you're decreasing entropy, you have complexity.
Yeah.
But you don't have something constructive which says, given any starting knowledge, I can construct the quick algorithm that will be maybe not optimal, but has a bound given by the second theorem.
Okay, so I think that here this is a general theorem. You're right that we do not construct AB in this theorem with this particular constant. I think it's 0.2 in the theorem if you want to check on the paper. But what they do in the paper is that they prove that the pair they are going to choose will decrease the entropy, not by 0.2, but by some constant. So actually, this theorem at the beginning was just general, like there exists one, we don't say what is the pair, but in this paper, they are able to build an algorithm that satisfies with another constant.
Yeah.
Okay, so they
So
show
Not necessarily for the best constant, but for some constant.
and so
And then you have an n.
given a starting knowledge, they have something that's asymptotically not optimal, but of the right order.
Yeah.
They prove that they have the right order.
Yeah, that's
Essentially.
Okay.
Yeah.
That's it.
Yeah. Thank you very much. Are there some remaining questions, in particular on the bridge?
So perhaps I start seeing the connection with the talk of Deria. And so this entropy, I just was checking, introductions were Kerner in information theory. And this is really when you have, this is about the compression of on the channel coding theorem. You have symbols, and you may have confusion between symbols, right? And you want to see at what rate you can transmit information, and this kernel entropy is the Shannon rate. And also, but she used it, I think, for compression also. But it's really the same thing. And so, what is surprising to me, don't see why. I mean, what is the connection between this compression entropy or channel entropy and this problem, right? Because what you do now is that you introduce an edge between 2 points if you have information on how they compare, right? And what is the connection between that and the compression? I don't see. Because you, on one side you want to compute the number of linear extensions, right? And you use entropy to diminish that, if I get it correctly. Yeah. And I don't see the connection with this. I mean, partial information on the order and this ambiguity in on these channels.
Maybe I can take a guess, which would be that. So here we're always making the switch between the poset itself and the incomparability graph. Okay, because the entropy that we are considering here, in fact, is the entropy of the incomparability graph. Okay, so when you don't have your information about two nodes, E and whatever here, E and H, for example, and you compare them, that will mean that you will add an edge in the poset, which means that you will remove an edge in the incomparability graph. So if you see it in terms of symbols and so on, it means that in some sense these two edges cannot be confused anymore, because you see what I mean?
Okay.
And I think that yeah, it's better in terms of information. You cannot confuse them anymore. You have the information that is needed to distinguish them. And I think maybe that's really a wild guess, but why it is entropy of the incomparability graph not a perfect tool for this question of sorting, is that here, in fact, when you have a poset, you have the notion of transitivity. So when you gain information about an edge, in fact, maybe you will gain much more information because of the transitivity. And I would tend to think that it is not taken into account. It's not very precisely taken into account in what you're doing with the entropy of the incomparability.
Okay. So perhaps what you answer is that perhaps this is a tool which works, but perhaps it's not the optimal tool. This graph, because the connection.
It's clear that it's not the optimal tool, because in the example that Emma gave, in fact, you cannot, in fact, taking in the middle or at the bottom, in fact, as Fabien noticed, is the same in terms of real information, of really splitting the universe into two, but the entropy tells you that it's not the same. If it was a perfect tool, it would tell you, okay, it's the same, you divide the world into. That's not what it does.
Actually, is it really the same? Because in the paper where I took the same example, which is another paper than this one, they said that it was worse to take this than this. And I was a bit surprised that I believed them.
I'm quite convinced by Fabien's argument that by symmetry,
you split the world in two.
You split the world in two.
The operations you can do to gain more information are not the same for every world. So you don't just want to split it in two, you want to split it into two worlds that are easily splittable down the line.
In the long term, and
And I
ideal,
think that's what the
but,
entropy is saying, is you're splitting it in two, but if you're doing it in the middle, those two are hard to split afterwards. At some point, you'll be in a state where extra comparisons won't split it into two.
maybe.
And so I think that's what the entropy is telling you is you're splitting it into two easily splittable worlds. So I think that's what it's getting at.
Maybe that's the another explanation.
And the entropy of your poset at any given time is how easily is it splittable down the line. The lower the entropy, the easier it will be to actually split properly. Because it would be interesting to see if there are cases where there's no good split, meaning you can't really split in half given any comparison. And that's sort of the key to what you're aiming to avoid down the line. My take on it. And coming back to the channel question, I feel like it's almost a error correction code that's hidden somewhere, where you have a noisy channel and giving an extra edge to the poset is basically giving one bit of error correction at a time, but those errors corrected in a weird way. And your entropy is how many bits do I need to add to correct the whole channel? But you have to choose them intelligently. So you're constructing an odd error correction code based on your initial channel state. I don't know if that makes sense as an interpretation in a way.
Yeah, it's puzzling, right? So, but there are two explanations. Either the one of that you gave, that perhaps, I mean, it's an ad hoc tool, it works, but we should not think too deeply, because I mean, it just otherwise
it's too good.
and the other one, there is something deeper, which is interesting. And so, there are these things. I mean, that's what ERC program is on that, right? And so our lecture was really based on this notion of entropy, but for reasons which were compelling, right? Because this really gave. You remember that she was computing functions. The two sources. She's a bipartite graph. She computes the entropy because there are two transmitters and a receiver. You want to compute a function of the two sources, right? And she computes the real entropy at which you can decode or compress or things like that. But and this was this kernel thing, which is the ultimate thing. That was the. And so either there is a deeper connection, which is interesting, or okay. So perhaps we could send this paper to her. We could ask her. She's the expert, right? We could ask her what she thinks, right, of the connection.